Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together.
Hello there. If you watched my last video, then you noticed that I started talking about how the relationship between roots and the factors of the polynomials happen to be, and that if the graph crossed the x-axis at x equals 3, then x minus 3 was a factor, and that f of 3 would have a remainder of 0 by that remainder theorem. And also that the degree of the polynomial matched the number of roots. Now, when I say number of roots, I'm not saying number of x-intercepts. I'm saying number of total roots. This would be real and complex. So this video is just going to go ahead and extend that and talk about how you might go about finding the roots without a calculator, because in the last video I used the calculator as a step, and that's just to make the video a little bit shorter. So let's go ahead and let's think about this equation right here. 3x to the 4th plus 4x cubed plus 2x squared minus x minus 2 equals 0. Well, we could grab the graphing calculator and have it do the work for us. There is something known as the Rational Root Theorem. Okay. I like to abbreviate theorem. And the Rational Roots Theorem is going to make a list, important word there, list, of all potential rational roots. And the key word there is rational. This is not going to get those complex ones. It's not going to get any of them with a square root. This is only going to get the ones that can be written as a fraction. So step one in defining the list, because if you can make the list, you can find the roots, is we're going to take the factors of our constant. Okay, factors that of 2 are 1 and 2. And we're going to put that over the factors of the lead coefficient. And that's that number in front of the variable with the highest power. The coefficient there. So our lead coefficient was 3. And it's the lead when you write it in descending order. So things that divide 3 are 1 and 3. Okay, so we're going to make fractions where the pink numbers are the numerator and the green numbers are the denominator. So my total list is positive or negative. Okay, that's really important. 1 over 1, 1 over 3, 2 over 1, 2 over 3. Those are the only 8 numbers that I'm going to try. Why do I say 8? 1, 1/3, 2, 2/3, -1, -1/3, -2, -2/3. This is our list. This is our multiple choice, basically. So even if you don't have a graphing calculator, you can now try to find your 4 answers. Okay. Why 4 answers? Because our degree is 4. Okay. So three x to the 4th plus 4, whoops, plus 4x to the 3rd plus 2 x squared minus x minus 2. 1 was not it. Two was definitely not it. That was getting really big. Okay. One third did not work. I like to arrow back to the beginning and do this. All right. Two-thirds absolutely did work, so two-thirds is one of our answers. Why did it work? Because it came out to have a remainder of 0. That's telling us it's a perfect factor. Okay, so now I'm going to try negatives. So I'm just going to go to the top one, and I'm going to put, oh, hey, come here. I'm going to put a negative in front of that. I'm just using the insert key, which is available even on like the basic TI scientific calculator. And -1 worked. And I'm kind of getting tired of trying these, so I'm not going to try the other 3. Because I need to show you what happens anyways, just in case the other 2 are not real. Remember, imaginaries always happen in pairs. And I'll explain why that is. Actually, it's because of the conjugate rules theorem. And it's because we have real numbers in our problem. So if you're down to just 2 answers, instead of just trying them, you don't know whether it happens to be a double root yet or whether they're imaginary. So that's one of those reasons why. That once I get all but 2, I'm just going to go ahead and go back to our faithful friend, synthetic division. So I'm going to do 2/3 first. I know some of you might avoid fractions, but it's really not a big deal. Bring my 3 down. 2/3 of 3 is 2. I'll add. 2/3 of 6 is 4. I'll add. 2/3 of 6 is 4. 2/3 of 3 is 2. And look at that. Our remainder is 0. Now just a quick note. If you ever have 2/3 as a root, your parenthesis is 3x minus 2. Because when we're factoring, we really don't want fractions inside. And if you set that equal to 0, you would add 2 and then divide by 3. So just remember that if your 0 is a fraction, it's because your quantity had a coefficient. We don't want fractions inside our quantities. Just isn't as nice. We like to use integers there. So 2/3, now -1. Bring down my first number. Multiply, add, multiply, add, multiply. I forgot to do that little line. And now we have a quadratic. We have 3x squared plus 3x plus 3 equals 0, and we can solve this by using the quadratic formula. However, before we do that, we're going to go ahead and divide by 3 to give our numbers smaller. And so x equals -b plus or minus the square root b squared minus 4ac all over 2a. -1 plus or minus, aha, there's that negative. I was not going to find any additional real answers with this. So we get -1 plus or minus root 3i all over 2. giving us our final answers of 2/3, -1, -1 plus root 3i over 2, and -1 minus root 3i over 2. Now, just a quick reminder in factored form, just in case you forget, we have this root of 2/3. We would not have x minus 2/3 as our parenthesis. We don't want ratios, we would prefer integers. So instead, I'm going to multiply by 3, then subtract the 2 over, and this would be my quantity or my factor. So just a heads up on that. The other thing is we synthetically divided by 2/3. We synthetically divided by -1. And we got down to 3x squared plus 3x plus 3. Now, if you're using synthetic division to help you factor, I get that we would have x minus 2/3. And I know I said don't do that. I'm going to show you where it comes from here in a second. So we would technically have those factors, but I'm going to GCF the 3 out of this parenthesis. And then I'm going to distribute this 3 into this parenthesis. So now we see 3 parentheses that are all relatively prime, meaning they don't have a GCF. And there we have our prime factorization. It's not a complete factorization because we still have an exponent, but it is our prime factorization. So keep in mind that yes, we have a fractional root, but that fractional root becomes because there was a coefficient. As you heard me allude to earlier, there is a conjugate pairs theorem. And anytime you have a polynomial with integer coefficients, your roots are going to have conjugate pairs. You're not going to have one without the other. So for example, if you have 1 plus the square root of 3i, you'll also have x equals 1 minus the square root of 3i. If you have 1 plus 5i, you'll have 1 minus 5i. If you have 2 plus the square root of 11, you'll have 2 minus the square root of 11. You won't have one without the other. So you might come across a problem that says, write a quartic or 4th degree polynomial. So they're asking us for an f of x. And then they're going to give us roots of 1 plus 5i and negative root 7. Of course, because we know that in order to have real coefficients, the first thing we're going to say, oh, is if we have 1 plus 5i, we're also going to need 1 minus 5i. If we have negative root 7, kind of like 0 minus root 7, we're going to have positive root 7. They always come with that plus or minus, and that's because we got these from the quadratic formula. Now these are technically x equals. So our parentheses are going to be where instead of it's x equals a number, it's x equals 0. So with the first one, I would have x minus 1 minus 5i. Now it'll equal 0. Then I'll have x minus 1 plus 5i. Now that equals 0. X plus root 7, and it equals 0, and x minus root 7. So when we multiply those 4 roots together, those 4 quantities, and reverse that zero product property, we will have our function. So we're going to have to multiply the first by the second, the third, and the fourth. And that'll get us our answer. Now, in previous videos, I've used grids to do this, like a 3x3 grid and a 2x2 grid to go ahead and multiply it. Here, I'm just going to go ahead and work straight across the page. So I'm going to multiply these 2 parentheses together first, and I'll do that in green, and I'm going to start by distributing the x through. So x squared minus x plus 5ix. Now I'm going to do the negative 1 through the second parenthesis, negative x plus 1 minus 5i, and then I'll do the negative 5i squared, or negative 5i. Sorry, I was getting ahead of myself in my brain. Minus 5ix plus 5i minus 25i squared. We'll simplify that in a moment. I'll do this one in purple, same thing. I'll work my way across, distribute the x. That way would give me x squared minus root 7x, and then distribute the square root of 7. Okay, minus root 49. That took up the entire page there, didn't it? Okay. Now we might notice that we have a positive 5x and a negative 5x. So those do cancel out and add to 0. We have a negative 5i and a positive 5i. Those cancel out and add to 0. We also have this negative 25i squared, but remember I squared is negative 1, so negative 25 times negative 1 is positive 25. So now if I take all the like terms and I add them together, I'll have x squared minus x and minus x gives me minus 2x, plus 1 and plus 25 gives me plus 26. And then from the purple, those two cancel each other out. So that will leave me with x squared, and this root of 49 is 7. Okay, this is much simpler now. I only have a trinomial times a binomial. So I'll start by distributing the x squared. That'll give me x to the 4th minus 7x squared. Now I'll distribute the minus 2x. Then I'll distribute the 26. And all that's left to do is to combine like terms. X to the 4th, check. 2x cubed, check. We have a minus 7x squared and a plus 26x squared, so we'll make that 19x squared. And then the linear term and the constant term. And there we go. Technically, that is our function. It said write a function who has roots. So instead of writing equals 0, I wrote it using function notation. So anytime you're giving the answers, you can work backwards to the problem and vice versa. The only thing that sometimes you won't know is if it has an a value. The only way to know that would be if they gave you a point that was not a root, and then you could solve for the a value. Otherwise, assume a equals 1 unless the directions tell you different.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? And drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.